So, a warm welcome back to our video lectures on projective geometry. This time we will enter a subject that I would say is very fundamental, deep and central with respect to our entire class on projective geometry. This time we will learn about so-called Cayley Klein geometries, and in a certain sense much of what we've done so far was driven in a way such that it's now comparably easy to introduce Cayley Klein geometries. So we will need conics, we will need different types of transformations, we will need projective invariants, we will need cross ratios. You will see how everything fits into one general framework when we consider Cayley Klein geometries. Let us start with quite fundamental question first. What is a geometry? So perhaps this question is close to being stupid because you are asking about a definition of a very general object, but let me at least spend a few thoughts on this kind of question. So geometry essentially is a system of several things playing together. So on the one hand, it's a system of objects like points, lines, conics, circles, and so on. On the other hand, you have relations between the objects. So a point may lie on a line or on a conic. You may have tangency between a line and a conic. You may have perpendicularity between some lines, depending on what kind of geometry you are dealing with. Then it's also, well, a system of transformations. Depending on what geometry you're dealing with, you may have projective transformations or Möbius transformations or Euclidean transformations. And then we have some point that we haven't dealt with so far. We have measurements. So perhaps the first thing you do when you do geometry is to measure things. So you measure perhaps the angles between lines or objects, or you measure the distances between two given points, or you measure areas of some polygons or ellipses or whatever. So essentially all these things that I've listed here, the objects, the relations between these objects, the transformations that leave certain aspects invariant, and the measurements are things that make up geometry. And so far we dealt a lot with the first 3 points and only very, very little with the last point here, measurements, which will change in a few minutes. One person who had some really groundbreaking and fundamental thoughts about what is a geometry was Felix Klein, a famous German mathematician. And in 1872 he gave a speech when he was appointed to become a professor in Erlangen. And in this speech, he presented his so-called Erlanger program. And this Erlangen program somehow turned these things upside down. It put transformations in the first spot. So essentially, a transformations is what defines a geometry. And it also focused on the central role of measurements, everything within the general framework of projective geometry. So the transformations he considered always were subgroups of projective transformations. And then, well, obviously he had systems of objects like points and lines, and we will later also talk about circles. And then he put measurements also into a very important state, and we will now really deal with measurements of distances and angles in these kind of systems. And the relations are still important, but I won't specify here what happens at that point. Before continuing, let me perhaps quote Felix Klein, what he said about Laguerre's formula. So you remember we had this formula for Euclidean geometry that expressed how you could measure the angle between two given lines. And once Felix Klein said about that formula, well, perhaps this formula is not that well known. At that time it wasn't well known because people have grown accustomed to the idea that projective geometry has nothing to do with measurements. And as a matter of fact, as we will see in a minute, the opposite is the case. You can use projective geometry to build really very far-reaching systems of measurements. You see two names up here. You see Klein and you see Cayley, and we also have to mention Arthur Cayley here at that point. He is more or less contemporary of Klein. He is a little bit older, and he perhaps was the first person who published what we will call Cayley Klein Geometries here, but in a kind of still too complicated way, and things were streamlined a lot by Felix Klein. So let us talk about measurements, and let me present the basic idea of Cayley Klein geometry, and you will see it is a quite simple idea. So what you need for a Cayley Klein geometry is you need a conic. And again, let me draw two pictures, one for distance measurements and one for angle measurements, but again you should think of those two pictures as being overlaid. So things that happen here and here happen essentially over the same conic. So let us define what is the distance between 2 points. So assume you are given 2 points, and for simplicity let's draw them within the conic. Then you want to define what is the distance between these 2 points. So what you do is the following. You draw, as a first step, the line between these 2 points and intersect this line with the conic. After that, you have 4 points on a line, and if you're doing projective geometry and you have 4 points on a line, what you always do is calculate the cross ratio. This cross ratio is now almost the distance between these 2 points, but we have to do some kind of cosmetic operation on that cross ratio. Cross ratios are multiplicative entities, so they behave nice under multiplication, and distances should be additive in a way. And to get from something multiplicative to something additive, we take the logarithm of the cross ratio. And then there is one more thing. It's a constant here. I call it C dist for distance constant, which is used, I would say, for cosmetic reasons as well, to push things into real numbers and rescale globally. We will come to that in a moment. So once again, you want to calculate the distance between 2 points, P and Q. You draw their connecting line, you intersect it with the conic, and you get those 4 points. You calculate the cross ratio, take the logarithm of that, multiply it by some constants, and what you get, call it distance. So take this as a definition, and we will see in a moment that it makes sense. And now for angles. And the beautiful thing about Cayley Klein geometries is that it is really a dual theory. So the angles are just the dual concept to distances. So what do we have to do? This time we want to calculate the angle between two lines L and M. Then we take their point of intersection first. As we took the join here, we take the meet here. Instead of taking the two intersections with the conic here, we take the two tangents, which is the corresponding dual concept. Now you have 4 lines through a point, and you can calculate the cross ratio. Again, angles should be additive rather than multiplicative. So we take the logarithm and this time multiply by a cosmetic constant, C_ank. And what you get, you call it the angle between L and M. So let me just summarize what you need to define measurements within a Cayley Klein geometry. So first of all, you need the conic, and this is really the essential part here, and I called it F this time, and F stands for fundamental object. This is a fundamental object defining your geometry, and it must be given by a suitable primal dual pair, because you have to deal with intersections and you have to deal with tangents. So for that calculation here, you need the dual conic, and for these calculations here, you need the primal conic. So both our conics here come from the same primal dual pair, and then you need your two constants, C_dist and C_ank here. And that's it. That's Cayley Klein geometry. And I could stop my lecture here because I said everything, except of I haven't told you why this is so cool, and it really is a cool thing. So let us step by step see how we can find geometries that we all know and even many more within the systems I've given you here. So for that, let me once more recall what we did when we classified primal dual pairs. So when we classified primal dual pairs, I told you there are 7 possible ways of getting a primal dual conic up to projective invariance. I already told you that this conic here corresponds to Euclidean geometry, and it actually corresponds to Euclidean geometry considered as a Cayley Klein geometry. And all the other possibilities here correspond to other types of geometry, and so we will have to analyze what may happen. So, but first we have to have a closer look on what happens here in these kind of measurements, because I've drawn the situations here in a way that may be a little bit misleading. It may be a little bit misleading because it doesn't point to the fact that interesting other situations may arise. So I've drawn P and Q in a way such they both were inside the conic, and so the join of them will always intersect the conic. And here I've drawn L and M in a way such they intersect outside the conic, so the tangents could always be drawn. This is not the case in general. Let me just move my objects a little bit. So it may, for instance, happen that the join of P and Q is tangent to the conic and that X and Y coincide. And it may dually happen that the two lines intersect on the conic and that the two tangents here coincide. And we may go even one step further, and it may happen, and you see I used the cross notation here again, that there is only a complex intersection of the line and the conic, and here it may happen that you only have complex tangents, and we have to deal with all these kind of cases when we study Cayley Klein geometries. So we will do that to some deeper extent now for the distances, and you should keep in mind that the angles are just a dual theory to what's going on here. So it's okay if we focus on the distances and from there then draw analogous conclusions for the angles. So one thing we should have in mind here is if you look at this expression here, you take the logarithm of a number, and you know the logarithm of a number also may become negative. It may even become complex, and we will have to deal with that case. But in the case when, for instance, X and Y are real points, you may have cross ratios here that may be bigger than 1 or between 1 and 0, and depending on that you will get either a negative or a positive logarithm. So what you actually get here along a line is a kind of signature for your length. So you will have positive distances and negative distances depending on your order. So if you concentrate just on a line, it's a good way to think about oriented or signed distances. Then I already told you, you have to consider three different cases. The case where x and y are distinct and both real, the case where they coincide and both are real, and the case where they are distinct and complex conjugates. So we will, in our next video lecture, go in depth into these three situations. And one more important thing that in particular plays a role if you are in the complex conjugate case. So the logarithm is defined as the inverse operation of the exponential function. And if you consider the exponential function and consider something like e to the I times an angle, then this is a periodic function, and in that sense the logarithm is a kind of multi-valued function, and so we may consider our sizes that we get here only be given modulo a factor which is c distance times 2 times I times pi, which comes from the multi-valuedness of the logarithm function if you consider it as the inverse of the exponential function. So let me just collect a few obvious facts that show that those kinds of distances I've defined here are reasonable objects. And mainly I will talk about the additivity of these distances. So first thing, if you calculate the distance of a point to itself, you will get a 0. Why will you get 0? Well, if you plug in p and p into the cross ratio with any two numbers, you get a 1, and the logarithm of 1 is 0, so the distance here you get is 0. Next important thing, I said we have oriented signed distances along a line. So if you reverse the order of p and q, what you will get is the negative distance. And again, this directly comes from multiplicativity of the cross ratio, because if you interchange p and q in your formula, you get the inverse of the cross ratio, and getting the inverses corresponds to negatives if you take the logarithm. Last thing also has to do something with multiplicativity. I introduced the point r in our drawing, and I now want to see how the distance of p to q and q to r relates to the distance of p to r. And what you get is such a nice additive relation here. And again, this comes from multiplicativity of the cross ratio because, well, if you calculate the cross ratio with p and r, you can easily check it's just the product of those two cross ratios, and after taking the logarithm, this product here turns into a sum for the distances. So by now I have shown you several, I would say, well, fundamental properties of your distances. And what we will do in our next lecture, and I will give a little preview, I will show you what happens if you walk in unit steps within such a geometry along a line. So assume you have a point P and a point Q, and you walk in steps of equal lengths in one direction, and what happens is what you see here in that picture. If you start at P and go to Q and take the same distance from Q to another point, and so on, you will get closer and closer to the boundary of your conic, no matter in which direction you go, but you will never reach the boundary. It's like you are trapped in the interior of that conic and never can get to the boundary. And let me just show you a few qualitative situations here. So what we actually really do, we calculate such equidistant steps here, and let me move the situation a little. So you see, if I move Q, you always have the situation that you are trapped within the conic. I did the calculations in both directions here. And now let me move the line to a different place. You see everything essentially looks the same. And now let me show you what happens if you go to the limit situation. So as a next thing, let me move the line in a close to tension situation, and you see that you almost don't get out here, and we will see to what that corresponds in our next lecture. And now let's get a little bit even more subtle and move the thing out, and you see you get really weird pictures here. And perhaps you notice best what happens here if I move to this position here. So you see, if you move in that direction, your steps get longer and longer, and actually they pass through infinity and come back from the other side. And you will see that in the situation where the line doesn't cut the conic, you will get a measurement that is like you're walking on a circle. We will analyze these three situations in detail in our next lecture, and after that make a classification of Cayley Klein geometries. See you there!